Okay, so nice. Welcome everyone. So today we'll have a Soham from USC to tell us about the Bohr-Sommerfeld profile surgeries.
Okay, thank you. Thank you for the invitation. It's a great honor to be speaking about my research here. And I think I'll see a lot of you in person next week. So yeah, excited for that. Okay, so today's talk is about Bohr-Sommerfeld profile surgeries. This is a type of surgery on Lagrangian submanifolds. And this is based on this work, which is on arXiv, and this is the identifier. All right, let's start with some history. So if you want to see history of Lagrangian surgery, you can trace it back to Polterovich in 91. And actually, Lalonde and Sikharov also did it simultaneously, but they did it for only Lagrangian surfaces, whereas Polterovich did it for any Lagrangian thing. So I think that's why we call it Polterovich surgery in like our literature now. So I'll start with the construction quickly. Polterovich surgery does the following. If you have a Lagrangian such that there is a self-intersection point P, such that it's an immersed self-intersection point of only two sheets, then you can take a Darboux chart of it such that near this singular self-intersection point, the Lagrangian will look exactly like Rn and IRn. So the real Lagrangian and the imaginary Lagrangian. Let's call that H naught. And what Polterovich surgery did was you replace H naught with H psi, which is a new Lagrangian embedding psi, where psi is an embedding of this sphere times 0, 1. So it's a cylinder of sphere such that the embedding near one of the ends, let's say at 1, the embedding is lying on the real plane, and on the other end, let's say at 0, is lying on the imaginary plane. So basically, what you're doing here is you take this cross type of singularity and you replace it by kind of smoothing. And the spheres here you should see as like near Sn-1 times 0, you're lying here. So like you have a spherical shell in the real plane and you have a spherical shell in the imaginary plane, and you're kind of joining them together smoothly. Okay. This process you can see is now creating a new Lagrangian where you don't have this singularity. And this is called Lagrangian surgery. And the way you do it is that since you had this Darboux chart so that this branch look exactly like this, you just replace using the same Darboux chart with this. Note that near the ends, it looks exactly the same. It's like these blue lines. So you can actually glue them smoothly. So you get a new Lagrangian. Okay. Now note that there will be a choice of this Lagrangian embedding, and there are two classes of this choice. For n equal to 1, it's very clear. If n equal to 1, your Lagrangians exactly look like this. This will be the pre-surgered Lagrangian. And the way to smooth it will be you smooth it in either directions. It could be in this direction or this direction. And they create different Lagrangians, as you can check on this figure 8 diagram. If I have this figure 8, this point here is the self-intersection point. You take a neighborhood of that. And if you do surgery in one way, what you get here is this, two circles which are disjoint. If you do surgery in the other way, you get like this wiggly circle. And it is true for any n odd, you change the topological type, but for any n even, you don't change the topological type of the Lagrangian, but it can still lie in different isotopy classes of Lagrangian, symplectic isotopy class or Hamiltonian isotopy class. Okay, so that was Lagrangian surgery as Polterovich did it. And after that, there has been more generalizations of that, or actually reverse direction things. In 2013, Meilin Yao constructed a thing called Lagrangian disk surgery. And it starts off with a Lagrangian surface. So let's say this tube is a Lagrangian, and you have this disk D, which is also a Lagrangian disk. And L and D, where intersecting, are only on the boundary of the disk. So the disk does not go and touch the Lagrangian somewhere in the interior point. The intersection is completely on the boundary of the disk. If you have a situation like this, and you assume that it is a clean intersection, Then Yao showed a way to construct a new Lagrangian L naught by shrinking the disk and introducing immersed point here. So this is this kind of figure of two planes intersecting transversely. And then you are at the stage where you can do a Polterwitz surgery. So note that Polterwitz surgery has two directions. One direction will come back to itself. The other direction will potentially create a new thing. This composition is called a Lagrangian disk surgery. So if you want to think of cartoons, it is you have this disk, you shrink this disk, and you create and expand a disk in a different direction, and you get a new Lagrangian with a new disk. This is Lagrangian disk surgery. And in 2015, Louis Hogg extended it to not just disk surgeries, but instead of disk, you can take Lagrangian balls of any dimension. So instead of D2, it will be Dn, and your Lagrangian will be any n-dimensional thing. Some other generalizations where in 2015, Chekukmark and Wewu did the clean intersection case of Polterwitz surgery. Similar starting point. Instead of an immersed point, you have a self-clean intersecting immersion on some Lagrangian, and they show you can do a slice-by-slice Polterwitz surgery to get a new Lagrangian. And in 23, in my first paper, I show a new type of surgery where you don't have these nice singularities, you have a conical singularity. This was a conical singularity on a Clifford torus. If you have a Lagrangian so that it has a conical singularity modeled on a Clifford torus, which will be clear later, then you could smooth it to something which is a cylinder times Clifford torus. Okay, this was like a short history. Of course, it's not exhaustive. There will be many more other surgeries maybe, but these are all the types of surgeries we have seen. It's always is like a generalization of Polterwitz surgery, except this case. This was some kind of conical surgery. And the effect of surgery on fluid theory has been pretty important. One of the most important thing for me is like Viana showed that there's infinitely many monotone Lagrangian tori in P2. By showing that you start with the Lagrangian, you do some disk surgery, then you get a different disk potential for it. And thus these two things will be different. And he shows that you can do it infinitely many times. And there is a rich structure of fluid theories, like the effect of surgeries on fluid theory. And this is again a partial list. So instead of going through what all of them do, I just wanted to like give scenery of what's going on everywhere in fluid theory of the surgeries. Okay, now I think I'm done with history and I can tell you what the result of today's talk is. The main theorem reads something like this. Under nice conditions, of course, I want to be vague so that it doesn't bog you down with details. Bohr-Sommerfeld profile surgery of a Lagrangian L with a lambda profile results in the following change of disk potential. And okay, so I should pause and tell you what this means. Bohr-Sommerfeld profile surgery is a new type of surgery which depends on this lambda here is a Legendrian. It's actually a Bohr-Sommerfeld Legendrian. That's why the name. And it'll be clear why I call it a Bohr-Sommerfeld profile surgery. So this surgery depends on lambda and creates a new Lagrangian. And if you have nice conditions, then, so this nice condition thing is only for this equality. The surgery always exists. So if you have nice conditions, the disk potential changes in this way. If you have never seen disk potential, it's just a polynomial associated to a Lagrangian. So this is the polynomial before surgery. This is the polynomial after surgery, and they are related, as you can see, by just changing one variable. The variable z is changed to z times some other polynomial, where this polynomial is a polynomial which only dependent on the profile I was using. And this can be thought of as a generalization of disk surgery, as we'll see. Okay. Some applications of this new result will be that you have new types of circle bundle lift, where when I say circle bundle lift, I mean what Biran did in 2001 and later in 6 and 9. Biran showed that if you have Lagrangians in symplectic divisor, then you can lift it to the bigger manifold. And I can show that whenever you have this Biran circle bundle lift, you can do a Bohr-Sommerfeld surgery, so you get a new circle bundle lift, which I call an exotic circle bundle lift. As a result of that, you see that there's new Lagrangian monotone tori in Pn, where I start with Vienna tori and take exotic lifts of that. These will be new. Some other results are like conical surgeries will be a new result out of this. A disc surgery was a conical surgery where you're taking a cone over a circle, but cone over a circle is exactly the disc. So conical surgery can be thought of as a generalization of disc surgeries, where you start with Bohr-Sommerfeld Legendrian, and if you have a cone, and then you can do, if you have the same setup of it hits your Lagrangian cleanly, then you can do conical surgery. And the last thing is that Akhtar, Course, Galkin, and Kasperik have this version of combinatorial mutation for Newton polytopes, which comes up and it is imported in mirror symmetry context. This surgery realizes it on the symplectic side. It was expected that if two LoRa polynomials were related by this combinatorial mutation, they should come from actually Lagrangians which change, are actually mutations of Lagrangians. So some of them were actually seen, like for Vienna's case or disc surgery, it was seen, but not all of the combinatorial mutations are known to be coming from Lagrangians. My result shows that some more of them are actually coming from such actual Lagrangian mutations. Okay, so now let's go to a heuristic of how to construct surgeries. So I've already told you what Polterowitz surgery does. Now I'll tell you how to get like a formula of how to do surgeries in general. If you have a setup like this, where let's say M is your symplectic manifold, and U is an open thing inside the symplectic manifold, such that the boundary of U has two parts, and both of them are contact. One is the positive part and one is the negative part. So you can think of U as a symplectic cobordism between du plus and du minus. If you have a Lagrangian L such that it intersects U and does not really go outside to the du minus part, and let's say the intersection of the Lagrangian L with the positive boundary is some Lagrangian lambda, then you can view inside U L intersect U to be some L plus, which is a filling of this Lagrangian lambda. Now, if you can switch, let's call that filling L plus. Let's say there is another filling L minus, which is filling the same Lagrangian. Then you can remove this filling, attach this new filling to get a new Lagrangian L prime, which is given by L prime is equal to L minus L plus. Okay. Okay, you can write out the gluing formula, like take that piece out, put it back in, but since you're gluing back only on the Lagrangian lambda and that is not changing, you will get another Lagrangian. And you can see that Polterowitz surgery does something similar. Here, U will be the symplectic ball, the Darboux ball. The boundary of the Darboux ball will be the standard contact sphere. The negative boundary is nothing because it's actually a symplectic filling. And you are actually taking different Lagrangian fillings of this Lagrangian. The real sphere inside the symplectic on the contact ball and disjoint union, the imaginary thing. And that is clear if you go back up here and see the boundary is the contact sphere. Rn intersects exactly on the real sphere, and IRN exactly intersects at the imaginary sphere. And you are actually changing fillings. You started with this immersed filling, then you have this two choice of fillings going this way or the other way. And this is how I will tell how to do a surgery. So to give you a surgery, all I need to tell you is what U I will take, what these fillings are, and what this Lagrangian is. So I will construct a Legendrian, two fillings of the Legendrians, and then it will be very clear of how to do the surgery, but just by replacing one with other. And something to note is that for me, U will be equal to Z times some A comma B, where Z is a pre-quantum bundle. Okay, I think now I can start talking about like some details and actual math. So let's start with Bohr-Sommerfeld Legendrians. Bohr-Sommerfeld Legendrians were introduced by Dimitri Gurizel and Golovko in 2019, and the construction goes as follows. The idea is you want to construct Legendrians in pre-quantum bundles starting from monotone Lagrangians in the base. So let's tell you what a pre-quantum bundle is. A pre-quantum bundle is a circle bundle over Y, where Y is a symplectic manifold, and the circle bundle has a connection one form such that its curvature is given by take just the pullback of symplectic form. You can check that this forces Z lambda to be a contact manifold because the curvature is pullback of a symplectic form. And not only that, you can see that the Reeb vector field is exactly given by the circle action. So our picture is like this. If this was Y, for a point over Y, you have a circle since it's a circle bundle, and the Reeb vector field R is exactly going towards the direction of rotating by the circle action. If you have never seen a pre-quantum bundle, this is the example you should keep in mind. This is a standard contact sphere with the standard contact form. This is a circle bundle over the projective space where the circle action is by half action. And you can check that d lambda will be equal to the Fubini-Study form. Well, this might be depending on which circle action you take. It will be either the plus circle action or the minus circle action, because you might want to think of S1 to be the circle bundle of O minus 1, thus this should be actually a minus. But okay, up to that change of signs, this is the main model you should have in mind. Okay, now I will tell you how to construct Legendrians inside this circle bundle. You start off with assuming, okay, for simplicity, let's assume that the symplectic form is integral and Y is simply connected. Now, if we have a monotone Lagrangian inside Y, the claim is that you can construct a Legendrian inside Z such that the Legendrian is a K2-1 cover. And we will see why we have this K2-1 cover. And the idea to construct this is we do a parallel transport. First thing to note is that since this is monotone, if you parallel transport along any loop gamma on Ly, then the parallel transport map is exactly on the circle fiber over P is exactly given by rotated by some rational fraction of 2 pi. So I should say that L comma K are integers. Yeah, okay. So the holonomy around gamma will always be rotation by some rational fraction. And you can see that K comma L right now is not unique, but you can take the smallest possible positive number K such that any holonomy PT gamma, which is just parallel transport around any loop, is rotation by e to the 2 pi L over K, where L is less than K. Forcing this constraint and taking the smallest K kind of forces what K is. It cannot be, it's well defined now. Now, what you see is that, okay, if I want to take a parallel transport, let's say I want to take a horizontal lift of lambda, why will this fail? Well, if I take a horizontal lift, if I go around here on the base, the point on the circle will go around and come back somewhere such that the angle difference is some 2 pi L over K. So you don't come back and close, but the way to fix it is to not just take one point, but take all the kth roots. If you take all the kth roots and go around, then this set of this kth roots will come, rotate and touch itself. So you actually see that the parallel transport is closed under, sorry, the kth roots is closed under any parallel transport. And that is the idea of constructing this lift. So I'll define lambda to be take the parallel transport of all the kth roots over fix a fiber, take all the kth roots, and you take parallel transport. By that I mean that lambda over a point Q is defined by take any path from P to Q and then take the parallel transport. And you can see that it does not depend on the choice of the path, because if you have two paths, you get a loop, and under that loop, this kth roots will come and just rotate by itself or not rotate at all. So you get that this is a submanifold just by choosing this set of k points. And now since I'm taking parallel transport, you see that locally, it is just a K to 1 cover because I'm taking K points over each fiber. And it's a Lagrangian because I am taking parallel transport, because that forces that lambda applied to this section is 0. It's actually taking a horizontal section, but a K-sheeted horizontal section of the Lagrangian. For example, if you take the Clifford torus inside P2, then recall that the circle bundle is S5. The Clifford torus will actually have a 3-to-1 lift, and it will look something like this. Okay, any questions so far about this construction? This idea of parallel transport will be used again. So if you have questions about this, this is a good time to clarify. If not, I'll proceed. One thing to note is that this lambda is not really unique, because the way you start is you first identify the fiber with S1, and this identification is not unique. It is unique up to some rotation. So this tells you that lambda is unique up to some rotation. And this is true because you could have chosen different kth roots of unity, like take the kth roots and shift everything by the same angle theta. And then you do this argument of parallel transport. You get a new Lagrangian, but everything is shifted by the action of e to the I theta. So what you actually get is that there is a family of Lagrangians, and this is exactly 0, 2 pi over k. Remember, 2 pi over k is, this number is here because if you start with the point here, I was taking kth roots. If you go all the way 2 pi over k, you will come back to the same point, like the same set. So there's only a family of this arcs amount, but then these two things are same, so you actually get an S1 family. So this S1 is like a shorter S1 than the other S1. Okay. Now I will tell you which Legendre I will use to define my surgery. The main Legendre for us will be lambda subscript 2, which is take lambda and take another copy of lambda, which is just go halfway up. So this was 2 pi over k. So I will say let's take the one which is given by going pi over k angle. This will be clearly a disjoint Legendre inside Z, and I will now talk about fillings of this. Well, what type of fillings? I should say that I'll look at fillings which are dimorphic to lambda times minus 1, 1. So this will be a cylinder's worth of filling. And this choice, you should see that Polterowitz surgery, I was actually doing something like this, where lambda was a sphere. And you will see that this is why we can recover Polterowitz surgery here. Okay, now I want to tell you about the fillings of lambda 2. So let's see where I will take the fillings. I will take the fillings inside R times Z. And note that since Z was a circle bundle, R times Z becomes a C star bundle. View the C star as R times S1. And I will now construct fillings by taking parallel transport with fibers in C star. Okay. How do I take fillings of this? So I want a filling such that, for simplicity, let's say the filling will be exactly equal to lambda 2 times 0 infinity. And the only things which change are inside the minus infinity 0 part. This is not important, but it's just to set a ground and have common language. So up to here, it's just same. So if you look at the fiber of the C star bundle, lambda 2 looks like this. Okay, there's a typo here. This should be e to the I pi o k lambda. Okay. 0 infinity times lambda will look like this. This is because on the circle you had 3 points, but now I multiply with R. So in the C star bundle, it is exactly the rays going out for lambda, and similarly for lambda 2. This will be, again, a set of rays going out, but shifted by pi over k. And I will construct fillings inside this C star by just telling you how to fill in the slice of C star, and then I'll define it by taking the parallel transport. Okay, so let's look at a C star slice. Okay, this is where the diagrams are not perfectly symmetric, but assume that this is Z3 symmetric. I'm taking k equals 3. So what I want to say is that if I apply e to the I 2 pi over 3, so if I apply rotation by third root of unity, this figure will actually go to this figure, which does not look like that, but let's be imaginative and say that it is Z3 symmetric. The way I do this filling is inside this circle, I join these by lines, and I can do this by joining curves such that it is Z3 symmetric. That I can always do. And there are two choices of joining by these curves. You see that these two things are not joined in this filling, but these two things are actually joined. So these two things are actually different fillings of the same Lagrangian. And I can now define the Lagrangian by just take this set of Lagrangian inside C star and parallel transport around Ly. This gives you some filling L plus, and the other one gives you some other filling L minus. So what I'm doing is I start with this rays, and I have two ways of filling. I can go this as one way, or I could go this as other way, and these will be my L plus and L minus. And recall that the heuristic needs three things: a Legendrian and two fillings. So I told you what the Legendrian is. It is this lambda 2, and I gave you two fillings, L plus and L minus. And now the surgeries, you just switch between one to the other. And I want you to see that this poltergeist surgery can be recovered by just take lambda to be the real thing. So to get the Legendrian lambda, you start with the real projective space inside CPN. That becomes a monotone Lagrangian inside CPN. The lift of that, the Bohr-Sommerfeld Legendrian lift, becomes a real sphere. And taking the halfway direction would be actually taking the imaginary sphere, because k will be equal to 2. So you will have a 0 to pi family, and taking here will be pi over 2, which is just I. So you will have the imaginary sphere here and the real sphere here, and there will be two fillings. As we see that in poltergeist surgery, there are two choices of smoothing. So I should say that BSP surgery with this profile lambda for lambda coming from RPN is actually a Lagrangian ball surgery, as one can define. Okay, so now let's talk about how to do this exotic circle bundle lift. So what Biran did was, if you start with sigma, a symplectic divisor in some monotone symplectic manifold, so M sigma monotone, and sigma is 4-dimension 2. And let's say you have a L sigma, which is a monotone thing lying inside the divisor. Biran showed that there is an embedding of a disk bundle. Sure, maybe change it to 1. So I'm viewing this as a disk bundle where on the 0 you do the standard identifications, and this is a circle bundle. So what I'm doing is 0, 1 times S1 quotient by something will be equal to the disk, where the quotienting is happening at when you have radius 0. Anyway, what Biran shows is that since you have such an embedding of a pre-quantum bundle Z over sigma, you can take the following thing. You can fix a radius R coming from this part, take the circle bundle Z, and then restrict it to L sigma. So what you're doing is you look at L sigma and take the circle bundle Z and restrict, and just take that for some specific radius R. What you get is something which becomes a circle bundle over L sigma and is Lagrangian. And by choosing this coordinate r precisely, you can make this circle bundle lift to be a monotone Lagrangian. Okay, now what you can show is that instead of taking just the circle bundle lift, you can take it and then kind of Hamiltonian isotope this circle such that it is Z over K symmetric. For simplicity, I'm choosing K equals 2. If K was 3, I could have done some figure like this. For K equal 4, I could do something like this. But you see what I mean. That for any rotation by K thing, you can always wiggle it so that each circle fiber touches transversely, which kind of means that the Lagrange is the contact thing Z transversely or cleanly on two Lagrangians. Now, if I do, we are exactly in the setting of doing a Bohr-Sommerfeld surgery. And if I do the surgery here, I had this filling inside and I can swap with this filling, and this would be the BSP surgery. So at the level of circle bundles, what you do is you have this circle, but you replace it with two circles, which are kind of symmetric by multiplying by some rational fraction. And the circle bundle would be replaced by taking parallel transport. And since you're taking parallel transport, these two circles will kind of twist around each other. Okay. And one important thing is that Bohr-Sommerfeld surgeries can preserve monotonicity if you have a circle bundle lift. And there's a way of saying that if you have these conditions, Bohr-Sommerfeld surgery will always preserve monotonicity. Okay, now let's go to some applications. So let's call B to be the Biran lift and E to be the exotic lift. So if you start with any T's ABC, where TABC is the Viana torus, recall that Viana constructed torus TABC for any triple which satisfies this. This is called a Markov triple. So for any ABC satisfying this, ABC integers satisfying this, you get torus. And Viana showed that if A prime, B prime, C prime is not equal to ABC, that would imply that T square ABC is not equal to T square A prime, B prime, C prime. Where this equality, I mean that there is no symplectomorphism of P2, which takes one Viana tori to the other. So this tells you that there's infinitely many because we know that this set is infinite. So there's infinitely many tori in P2. And one can just keep taking Biran lifts of them and construct lifts of that. This will be T3. So you start with T2, then you get a Biran lift, which is T3, and then you can do this again. You'll have a Biran lift, which is T4. And you can do this for any ABC. So for any Viana tori, there will be this sequence of lifts in higher and higher dimension projective space. So this is sitting inside P3, this is sitting inside P4, and so on. In 23, me and my collaborators, Amanda Hershey and Luya Wang, show that if you take these Biran lifts, then the Biran lifts will also not be symplectomorphic to each other. So there's no symplectomorphism taking T bar ABC to T bar A prime, B prime, C prime. So this equality is up to symplectomorphism. So this shows that there's infinitely many things inside Pn for any n, but that is not the whole thing. What one can do is, instead of taking just the Biran lift, you can now go take the exotic lift for any of these stages. Like start from T2, take an exotic lift. This lies inside dimension 3. Start from T3, then you'll get something inside dimension 4. And then you can form this kind of branching of taking lifts of either you take a Biran lift or an exotic lift. So you'll get this huge graph. So what I can show is that whatever you get here, these exotic lifts, let's call them T twiddle 3 ABC, T twiddle 4 ABC. So a T twiddle is start with some Biran lift, then apply one exotic lift. What I can show is that all of these things are new and they are not same with anything which we already saw. And two exotic lifts will also differ if their base points were different. Okay. Now, something which I do not know is what happens to the disk potentials when you apply it multiple times. Like potentially there will be 2 to the n many distinct things when you go up to n steps here. So this is something I'm not sure whether if you go exotic and then go Biran and go Biran and then go exotic, do you get the same thing or not? This is some combinatorics I have to figure out. But as of now, you get twice as many new things. Okay. So that is all the geometric things I want to tell you. Now let's go to the floor theory side. So I'll quickly recall what disk potential is. Disk potential is, if you've never seen it, all you should know right now is it's a polynomial on this space. This is the space of homomorphisms from H, the first homology of the Lagrangian, to C star. And let's assume this is torsion free. So this exactly becomes C star to the rank of the first homology, the first Betti number. And this polynomial is given by some count of holomorphic disks. So let's fix some almost complex structure J, which is compatible with your symplectic form. Let's fix a point P on L and assume L is monotone. Then the polynomial is given by this formula where you're counting Maslov two disks such that the Maslov disk passes through the point P on the boundary and U is J holomorphic. You can see that asking a Maslov two disk to pass through a point on the boundary, specific point on the boundary, becomes a virtual dimension 0 problem. So you can actually count them. So this is actually a finite sum. And for every disk U, if you write out the boundary of U in terms of some basis of H1, let's say it is V1, E1 plus V2, E2, blah, blah, blah. Then the polynomial, the monomial U2 is X to the X1 to the V1, X2 to the V2, blah, blah. As an example, you should think of the Clifford and Chekhov torus, and the potential for them are these. For the Clifford torus, you have its X plus Y plus 1 over XY. For the Chekhov torus, you have X plus this binomial thing. And this just means that X just means that there is some holomorphic disk such that the boundary of U is exactly 1 times E1, where E1 is like dual to X. And there was another thing in the theorem, which was the augmentation polynomial. I will not tell you exactly what it means, but all you should know is that it is a version of disk potential, but it counts punctured disks with the puncture going to a reed chord. And this polynomial is a polynomial on Hom of H1 lambda. So this is a difference, that it takes cycles inside lambda, the Legendrian, not the Lagrangian, and it assigns it to some complex number. And one thing you should know is that the augmentation polynomial can be recovered from the disk potential of the base. So I should cite this. This is with joint work with me and Kenneth Blakey, Chris Woodward, and Johan Sun in 23. And this is true only for, let's say, we only know it for Bohr-Sommerfeld Legendrians. I'm not sure what is the state right now for any general Legendrian in higher dimensions. Okay, I told you that it can be recovered. So let me just tell you how to do it by giving you examples. The disk potential of the Clifford torus, as we saw, was xy plus 1 over xy. The augmentation polynomial for its lift will be x1 plus x2 plus 1. And these two polynomials look pretty similar. And the similarity will be clear if you see the Chekhov torus. The Chekhov torus was x plus this binomial thing. And for the lift, the augmentation polynomial was x1 plus this binomial thing. Okay, now I'll tell you how to see these things. The formula from going from here to here is first write this as take 1 over xy common, then you will see it is x squared y plus xy squared plus 1. And now I can define x1 to be x squared y, x2 to be xy squared. Then you see that this is x1, this is x2, and this is 1. So this thing sitting inside here is exactly equal to this. And there is a general formula of going by take some coefficient common out and then do this algebra and do some change of variables and you get the augmentation polynomial. This might seem weird if you're seeing it for the first time, but something you should note is that the lambda Clifford torus for dimension 2 was a 3-to-1 cover. So this was a 3-to-1 cover. And that is why I am taking x1 to be x squared y. The cycle x does not really lift to lambda, but the cycle x squared y will lift to lambda. So that is why there's this change of variables. But these details are not that important, but all I wanted to explain was that I can rewrite w lambda in terms of w ly. Now I can get back to the theorem. So some of the conditions for the nice conditions, some of them are like very basic and expected. I want the Lagrangian to be monotone, compact, oriented, spin, blah, blah, blah. I will tell you the things which are new, like things which is not standard. First, I need to assume that the profile I was using, it was a Bohr-Sommerfeld profile over some Lagrangian Ly. I want this Ly to have enough regular disks. This is quite essential for my proof strategy, but maybe this can be improved later. By enough regular disk, I mean that there is a G which makes any Maslov 2 and lower disks regular. So there's no negative Maslov things, and Maslov 2 things are regular. And for that J, given any point and given any M, there exists one regular J-holomorphic Maslov 2M disk passing through the point. I'm not saying that everything is regular. I'm saying give me a point, give me any Maslov number, then there will be a regular thing passing through it. The good thing is that T squared ABC has enough regular disks. So I can apply my theorem. And you can also see that if you have regular disks, then every Biran lift will have regular disks. So you can keep on showing that the lifts, Biran lifts also satisfy this property. The second thing is that I want lambda to be homeomorphic to Ly, just to be in the simple setting. But I think you can remove this. But anyway, this is true when we have torus, because the torus cover will also be just a torus. And the last thing is that I want the Lagrangian L. So this is sitting inside some manifold M. And I want this L plus to sit in the following way in the homology. I want the homology of the first homology of the Lagrangian L to split. So L plus is sitting inside L. So I will have H1 of L plus will have a map inside H1 of L. And I want this to be a split injection. So this splits off as H1 of L plus. Then since it will have some Lagrangian which is orientable, and you can see that there will be a Poincare dual to it. Let's call that Poincare dual to be Z. So Z will be a cycle which kind of goes in and comes out. And W will be all the homology which is kind of away from where I do surgery. And recall that L plus was diffeomorphic to lambda times 0, 1. So L plus is exactly H1 of lambda. So with this convention, now I can tell you more details about the theorem. Here, these coefficients were coming from H1 of lambda. This thing which was changing was coming from the Poincare dual, and these other things were coming from things which were away from the surgery. And this is expected because if you have a disk which is geoholomorphic and is sitting away from the surgery, I am doing the surgery is here, but this geoholomorphic disk will be still preserved once you do surgery, because the Lagrangian is not really changing here. So any disk like this persists under surgery. The only thing which actually changes is like if you have a disk which kind of goes in and comes out like this disk will now have to kind of go inside L minus. So the coefficient corresponding to Z will have to change. And that is why we see that Z was changing. And there are no actual disks completely lying inside the symplectization part because lambda turns out to be exact. So there will not be any disk completely lying inside there. So the only things which occur are Z with maybe they twist around the lambda part while coming out, and they will change. Okay. So now we have an understanding of what the disk potential formula is doing. It is keeping almost everything same except this Poincare dual, which gets multiplied by this potential augmentation polynomial. Now I will tell you how to see that there is a new, I will tell you how to see there's one new monotone tori. So for that, let's apply the theorem directly. This is the exotic lift of the Chekhov torus inside dimension 2. So exotic lift of T2 Chekhov. And the potential formula tells you that it's related by this. And recall that the augmentation polynomial for the Chekhov torus was exactly this. So this is W lambda 2 Chekhov. So to get the polynomial for the exotic lift, I take the Biran lift and do this change of variables. And now I have to see that these two polynomials are actually different. And the way to see this is kind of hard if you just look at the polynomials. And the tool to use here is Newton polytopes. And they are like simplifications. They are exactly polytopes, and seeing two polytopes are different is easier than saying two huge polynomials are different. So let me tell you what a Newton polytope is. Given any LoRa polynomial with R coefficients, okay, this doesn't really matter. It could be any field coefficients. The Newton polytope is the following. You take all the tuples V1 up to Vn such that the coefficient of that monomial is not zero in the polynomial. So let's do it for the potential for Clifford torus. We know that the potential for Clifford torus is x plus y plus 1 over xy. Now x is same as x1, y0. Y is same as x, y1. And this is x minus 1, y minus 1. So I will now look at these exponents and just point on R2. So this corresponds to the point 1, 0, this corresponds to the point 0, 1, and this corresponds to the point minus 1, minus 1. And the Newton polytope is take convex hull of these 3 points, so you get this triangle. So if you have polytope, you have a bigger polynomial, you'll have more points, you'll have a bigger polygon. And if you have more variables, you have a polytope instead of a polygon. Something to note is that if Newton polytope of WL is not equal to Newton polytope of WL prime, that would mean that L is not equal to L in up to symplectomorphisms. And here this inequality is up to affine transformations. So of course you can change basis and then two polytopes will look different, but let's say you do not change basis. So like up to GLNK, GLNZ transformations, if two polytopes look different, their Lagrangians will also be different. So I will use this strategy to show these lifts are different. Okay, oh, this shouldn't move. I will just tell you what the Newton polytope of the Biran lift was. So this is from this 23 paper. And the polytope looks exactly like this. This is a z direction, this is the x1, x2 direction, and the polytope for the Biran lift was of the Chekhov torus was you have a triangular face. These red dots are the integer points. They correspond to the monomials. So the base of the triangle has exactly 4 integer points, and the vertex of this tetrahedra has 1 point. And I also know important things like the z coordinate for the vertex is z equal to 3, so it's lying in this z equal to 3 plane, and the base of the triangle is lying in the z equal to -1 plane. Now let's see what happens to z equal to -1 under this transformation. So I know the transformation will be z goes to z times the augmentation polynomial. Then z inverse would go to z inverse w lambda inverse. So this triangular face was exactly w lambda over z times some x alpha y beta. Okay, x1 alpha, x2 beta. The x part does not really matter, but what you should see that this thing would now change to w lambda divided by z times w lambda, which just becomes 1 times z. So this z inverse w lambda inverse is exactly this, and these w lambdas cancel. At the level of Newton polytopes, what happens is this triangular face shrinks to 1 point. This just becomes this monomial x1 alpha, x2 beta over z. So this was the triangular face. Now it becomes this one of this monomial. But the top point z equals 3 will go to z3 times this monomial to the cube because I had z3. What happens at the level of polytopes is that this point expands into this big triangle, which has exactly 3 times the Newton polytope of w lambda, and it will have 3 times as many integer points. And you can see that these two polytopes are not same because just the number of integer points are different, and number of integer points on each face is an invariant up to change of basis. And you can see that if you start with not just Chekhov torus, but you have ABC, then the lifts will also be different by just looking at the Newton polytopes. Okay, so this tells you that you get new Lagrangians by taking exotic lifts. And for the last bit, I can just do a very impressionistic painting of what the proof goes like. It is, you're changing L only in this truncated symplectization. So you want to study holomorphic disks and see how it changes if you do L plus to L minus. The idea is do a neck stretching, which separates the area of surgery. I do a neck stretch simultaneously at A times Z and B times Z. So I make these two necks thicker and thicker and take a look at the building. Now, there's a theorem which says that the disk potential can be recovered by counting rigid holomorphic disk buildings. So if I do next stretch here, I will have L plus here, and I'll have some outside manifold L out. And this in the negative part, there will not be L, L will be empty here. The main part is to classify rigid disks, which has boundary on this part. This classification result is the hardest part. And one shows that the only rigid disk which can occur will look like disk which breaks off at a reed chord, where this reed chord is the smallest possible reed chord. And this lets you now say that, okay, if I change L plus to L minus, I need to know fillings of the smallest reed chords. And I can just compare this holomorphic disk fillings of smallest reed chord. And by comparing them, comparing these rigid disks, you get this change of potential formula. And the main thing here is that the only rigid disks which occur, let's say this was a rigid disk which goes to this reed chord gamma, they will project to either a Maslov 0 or Maslov 2 disk inside Y. Maslov 0 disk is actually just a fixed point, so there's no disk, it's just a point you're lying on a fiber. And a Maslov 2 disk is the potential of Y, of Ly. And that is why you see this disk potential or augmentation potential show up. Okay, I think I'll end here. Thank you for patiently listening.
Okay, let's thank Soham. So any questions?
I have a fairly naive question. Since I've probably seen disk potentials in like other talks, but like the fact that it's called potential, I wonder if there's like a notion of like which ones have greater potential and if that's like reflected in your Newton polytopes, and also like how like is that a thing and is that reflected in the polynomials?
I'm not sure if, okay, I don't know the history or the terminology of why it's called a potential. It's called a super potential in the physics side, and then it's changed to disk potential and symplectic side. But I'm not sure if there's an ordering. Apart from like this count,
Okay.
how many things are, that will be there. But yeah, I don't know a physics way of saying this. Yeah, thank you for the question. It's a
Okay.
good question, but I need to look up.
So I also have a question about potential. So are these invariants?
Yes. Yeah.
So independent of a choice of J.
Yes. It is invariant up to symplectomorphism. Two Lagrangians which have different disk potential cannot be mapped from one to the other by a symplectomorphism. Because if you have a J, you can push forward that J. Okay, up to, of course, change of basis. Yeah, yeah. You can rewrite the polynomial by rewriting your variables. Up to that, it is invariant.
So what's the setting that under, so if it's a monotone or something like that, it's always a invariant, or
Yeah, yeah, okay. I should say everything I'm talking about is monotone. Yeah.
So the disk potential is not well defined for non-monotone, right?
Sorry, I couldn't get the question. Can you repeat that?
Sorry, for non-monotone Lagrangian tori, is there a well-defined version of a disk potential?
Well, yeah, then then this potential, you can think of it as like the mu0 term in the Foucault algebra. Like for a non-monotone thing, the Foucault, if you have a weakly unobstructed Lagrangian, then it will have a mu0 term, which exactly counts this thing. Now, how, like whether that thing is invariant up to Hamilton anisotropy, how much of that is known is something I'm not very up to date on. But it is exactly the mu0 term of the curve Foucault algebra, which is invariant up to some choices, but maybe not Hamilton anisotropy.
so in general, like given two almost a complex structure, both regular, how do you show the counts are the same? Yeah.
Well, you can take a family, and since you're having monotone things, you cannot have disk bubblings in a generic family. So you actually get a cobordism. Now you just see.
There can be J which is not transverse, right, in this family.
Sure. But it cannot have positive energy because you have monotonicity. So a bubble cannot form because every bubble with positive energy has to be of Maslov 2 thing, but you're starting from Maslov 2 thing.
I see.
I have a question on this, just on the current page.
This page?
Yeah, just current page. There's a count rigid holomorphic disk buildings. So is this part easy to be done, or it's difficult?
The classifying part or
Yeah, the count of rigid holomorphic disk buildings in the middle of this.
Oh, okay. So the statement I want to say here, the precise statement would be that count of rigid holomorphic disk recovers the disk potential. And the idea is that, okay, you have, let's say this was a rigid holomorphic disk, then you can do SFT gluing to get something actually holomorphic inside long T stretched manifold. This is, let's say, minus T comma T times Z. This theorem is kind of like the fact that you can recover it is kind of standard in the fact that, okay, if you have a rigid thing in a family of T stretched thing, it will go to a rigid object just by index count, and you have the reverse direction of gluing. And Chris has shown that this, in the case of where the contact thing is actually pre-quantum bundle, this is actually a bijective map for a large T. Was this the question? Like this theorem or the application of it?
Because this one involves Lagrangian boundary, right? This you have this Lagrangian boundary in this picture.
Yeah,
So
you have a Lagrangian boundary going there. Yeah.
Assuming this is harder because you have in this Lagrangian picture you do have this boundary manifold.
Yeah.
So
You have a
in this
Lagrangian boundary.
classification of rigid disk, so is it more or less explicit by the boundary condition?
Okay.
Any way to control it? So otherwise, I don't know. I just want to know how difficult it is on this middle piece.
Yeah. So for this middle piece, the main thing to note is that we'll fix for J equals this cylindrical J, and the middle piece is just R times Z, and the Lagrangian L plus would now, if you take the projection to Y, this will go to Ly. And the idea is to see that the only things which come with the smallest reap chord, if you have a disk where this gamma was the smallest one, then disk will project into something here. So how easy it is? Okay, I would say that there is a theorem which you have a holomorphic line bundle with fibers which look like this on the boundary. So this will be the Lagrangian boundary condition on the fiber, and this is C star. With this condition, O had this result where, okay, if you have a holomorphic line bundle with a totally real boundary condition, which is just real planes on the boundary, then this is holomorphically equivalent to something similar with the same Maslov index. So O's result was given to same Maslov index, totally real boundary condition. There's a holomorphic way of identifying them. So I had to change that to, instead of having totally real boundary condition of lines, I have to do it for totally real boundary condition, which looks like these kind of curves.
Mm-hmm.
It is kind of difficult. I would say that is the most difficult part of the paper. So for me, it was difficult.
Mm-hmm. So you can at least know the index, at least.
Yes. So yeah, there's actually just a classification of all disks, because any disk here will project to disk here. And similarly, any disk here, you view this as if you have a disk inside. Okay, maybe I should write this down. If you have a D2 y comma Ly, over this you have Z comma L plus. Let's call this map U bar. Then you can pull back this circle bundle. Okay, maybe not have Z. Let's have R times Z. So this is a C star bundle. Then you can pull back R times Z. And you can also pull back this as a fiber bundle. This pullback thing is actually C star bundle over Z over the disk. And on boundary, you have the data of there exists Lagrangian boundary condition.
Mm-hmm.
So let's say you have, okay, maybe here is a better way to. You have this disk, U bar. For each point on the boundary, you will have this data of, okay, sure, you have a C star fiber. But not only that, you have this boundary condition, which looks like the thing I showed, like this is like this curves joining the Lagrangians. So for each of these points, you will have a copy of them, and they're slowly rotating depending on the Maslov index. So if this Maslov index was 2m, this rotates, I think 2m times or something, or m times. So I have a result like this. So now you want to classify disks of this bundle, where the boundary is like this copy of curves inside C star, and it's slowly rotating. And that can be done.
Thank you.
Any other questions? Let's thank Soham again.